into how spring forces interact with what we've been doing. Just remember these facts about springs that we've talked about before. When a spring is stretched, it exerts a force tending to restore its original length. That force is proportional to the amount stretched. Doubling the stretch doubles the restoring force. It is, in math terms, a linear restoring force. The strength of a spring is indicated by a number called its spring constant, usually symbolized by K, and measured in newtons per meter. And why do we call it linear? Because the force is proportional to the stretch. If we were to map the stretch and the force, we would get a line. This equation also gives the magnitude of the force when the spring is compressed. So, if we track the position of a mass spring system on a low frictional horizontal surface, we see the pattern shown over here. This is a position graph that's been rotated by 90 degrees just to match the horizontal motion of the object as it goes back and forth. We want to say that it starts over here and kind of moves back and forth. This is sort of like a strip graph going down this way. It's really just a position time graph that's been rotated. The motion is again sinusoidal, and the object reaches what are called turning points as it comes to rest at x equals plus or minus a, and then turns around. So the name's not all that clever, but we can see that this is simple harmonic motion. And in fact, and this is important, oscillation about equilibrium position with a linear restoring force is always simple harmonic motion. The mathematics of it indicates anything that deviates from equilibrium in a way that it tends to get back towards the equilibrium according to a linear force is always going to be sinusoidal. Now, for a spring mass system on a horizontal surface, it was pretty easy to see the motion was simple harmonic motion. What about a spring hanging vertically, such as shown on the left here? Note that the equilibrium point of the system is no longer the unstretched length of the spring. Equilibrium is where the force is zero. On the horizontal surface, the force would be zero when the spring isn't stretched because it doesn't want to go anywhere. But on the vertical surface, on a vertical spring, that's not true. If we were to hang a mass here, the weight will pull it down and the spring is exerting no force upward, so it will move downward. And if we were to stretch it all the way down here and let it go, then there's a mass pulling it downward, but the spring is trying to pull it back up and will outweigh that and pull it back up. There will be a place where if we hang it, the spring force exactly equals the weight. So Newtonian analysis tells us that K times the new shift, K delta L, is m times g, which means the equilibrium has shifted by this, that delta L is mg over K. There's not a lot of depth there, nothing to really worry about. We're just saying this is going to be the place where the forces are in balance, which means if we place the mass at this delta L, then we will have equilibrium because there'll be no net force and it will just hang there. Or you could turn around and say where it just hangs is the shifted equilibrium. Sort of as an aside, we could turn around to get K instead. We could measure delta L after hanging a known weight on the spring. K would be mg over delta L. Experimentally, we wouldn't do it this way because there's a lot of uncertainty, right? We don't know what m is, we don't know what delta L is, we don't know what their uncertainties are. Instead, we'd measure delta L from any values of m, and then plot delta L on the vertical and mg on the horizontal. And we can see that the slope would be 1 over K because of L is 1 over K times mg. So if we make that our horizontal and that our vertical, then this is the slope. And I mentioned that not entirely randomly because we'll do that in a lab. So let's set our origin at the new shifted equilibrium point. If we move the mass up a little bit from that equilibrium point, the spring is still stretched a little bit. And the weight, of course, is still what it was. It's going to exert less of a force upward than it did here because it's less stretched. So if we go over all of this, we can say that there'll be a net force downward, which is not surprising. Let's compute that net force by saying it's going to be the difference of the upward force of the spring minus the downward force due to gravity. And the upward force is K times the stretch in the spring. Well, if this was delta L, but we've given back Y, then the stretch in the spring now is delta L minus Y. We can group these any way we want, so we'll have K delta L minus mg grouped, and then left over is minus ky because we can't do anything with it. But remember, delta L was just mg over K, and the K is canceled, so this parentheses is just mg minus mg, or 0. And meaning, most importantly, that the net force in this circumstance is minus ky. but that's a linear restoring force. So again, we have an equilibrium position where when we deviate, we're restored with a force of k proportional to the deviation. This is simple harmonic oscillation, just like the horizontal case. Gravity here doesn't affect the nature of the motion, it just shifts the equilibrium point. That will lead to some interesting things when we talk about energies, and just as a sort of foretaste, it means that we won't care whether the oscillating system is vertical or horizontal, because all that ends up doing when we orient it vertically is shifting all the energies by some amount, which doesn't actually change anything.